Okay, and now let's talk about deadlock. So, as I mentioned, deadlock is a unresolvable situation where there's a cycle of waiting among some set of threads, where each thread is waiting for another thread to uh, take some action or release some resource, and everyone is kind of waiting on each other, creating a deadlock in the system where the system cannot progress, and all the threads cannot execute because they're waiting on each other. Okay, so we then have these four necessary but not sufficient conditions for deadlock. And what does that mean? Um, in order for deadlock to occur, all of these conditions must hold. Um, but if we have all of these conditions, there is a chance we get lucky and don't have deadlock. And we'll see how that could happen later on. So, what are these four conditions? First, we have mutual exclusion and bounded resources. What does that mean? Well, that means that we have a finite number of threads that can hold a resource at the same time. And we also have a finite number of resources. So if we take a very simple example of locks and let's start there, only one thread can hold a lock at a time. And so that's an example of mutual exclusion because only a finite number of threads, in this case, only one thread can actually hold the lock at a single time. Additionally, anytime we're talking about resources, whether it's locks, semaphores, memory, etc., um, note that typically these are going to be bounded um, because we cannot just have an infinite number of resources for the OS. Yeah, so hopefully the bounded resources part makes sense, fairly intuitive, and yeah. Now the second condition is called hold and wait, and this is where um, threads hold on to a resource while they're waiting for another resource that's held by somebody else. So everyone's kind of holding onto one thing, waiting for another, and so they all end up waiting for each other, and nobody kind of wants to be the first to compromise and give up their resource to somebody else who needs it. And now the third condition is that there is no preemption in the system. And what that means is that once a thread acquires a resource, for example, a lock, its ownership is not going to be revoked or taken away until the holder acts to release it themselves. And so, yeah, a lock is a pretty classical example. Typically, once a thread acquires a lock, it's not going to, or nothing else is going to release the lock besides the thread itself when it no longer needs it. And that is going to cause an issue for us later on. And yeah, we'll see how that works very shortly. Okay. Now, circular waiting is the last and probably the most intuitive condition for deadlock, which is where there's a set of threads where each thread is waiting for a resource held by a different thread. And now to put these four conditions in more perspective, let's take an example called the dining philosophers example. And in this problem, we have five philosophers who are sitting at a table that each want to eat their meal. We have five chopsticks. And so, in order for any philosopher to eat their meal, they need to be able to hold two chopsticks at the same time so that they can actually eat. Now, in this case, suppose that each philosopher picks up the chopstick to their left, then tries to pick up the chopstick to their right, and once they are finished eating the meal, they will put down both chopsticks. Now, what is a potential situation that could result in deadlock in this example? Well, if you consider the case where all five philosophers pick up their chopsticks at the same exact time, or their left chopsticks, sorry, then all five chopsticks have already been picked up. But no philosopher has two chopsticks to be able to eat their meal with. And so each philosopher has one chopstick, but they're waiting for another philosopher um, to be able to obtain the second chopstick. And so everyone is holding one chopstick, waiting for another. That's the hold and wait component of the four conditions. And so we end up with a deadlock unless somebody gives up their chopstick for another philosopher to use. Now, the last thing I said is part of the no preemption condition. So in this example, deadlock is possible because we assume that once a philosopher picks up a chopstick, they're not going to put it back on the table until they've finished eating, and they need two chopsticks to be able to finish eating. If instead we allowed a philosopher to put down their chopstick, if, for example, they picked up the very last one, then someone else would be able to pick up two chopsticks at the same time, right? So one from their left, another from their right, from the philosopher who put down their uh, chopsticks when they saw that it was the last one on the table. And the philosopher who now has two chopsticks will be able to eat their meal, finish, and put the chopsticks back down on the table for somebody else to use. So that is if we did have preemption, and that would allow us to get out of this deadlock. But if we do not have preemption, where we establish that each philosopher is going to, wait to finish eating before they put down their chopstick, then deadlock occurs. Okay, so I went over two conditions, the hold and wait and the no preemption. And now circular waiting, you can see um, how this is applicable in this example, since we have five philosophers, each of which is waiting for the philosopher on their right. The last condition that I didn't go over is mutual exclusion and bounded resources. And so here, the reason we have mutual exclusion is because we established that each philosopher can only hold one chopstick at the same time, right? And it wouldn't make sense for two philosophers to share one chopstick simultaneously, right? So if that was the case, we would not necessarily have deadlock, but we did establish, or I guess I didn't specify this, um, but we do establish that each philosopher or each chopstick can only be used by one philosopher at a time, and so we do have mutual exclusion. And of course, the bounded resources part comes from the fact that we only have five chopsticks. If we had six, we may not have this issue. Or, really, if we had infinite chopsticks, we wouldn't have this issue. So, yeah, hopefully that makes sense. So these are the four conditions. We will also go over a case where these four conditions all are in place, but deadlock does not occur. And I can actually give an example with the philosopher's problem over here. Now, the reason that we had deadlock before is because we specified each philosopher tried to pick up their chopstick to their left first, and then the one to their right. And all five philosophers picked up the chopstick to their left simultaneously, or at least they all picked it up before they had the chance to try and pick up the chopstick to their right. Now, consider the case where, maybe some philosophers are yapping away and they're not paying attention. And so they don't try and pick up, both of their chopsticks. And so another philosopher who is trying to eat is able to actually acquire both the chopstick to their left and right? So, you know, maybe I'm yapping away, I'm not paying attention to my plate, and say Jacob's sitting to my right, and he's able to pick up the chopstick to his left and right, so he can finish eating, put the chopsticks back down on the table, and then I can pick up the one that he's no longer using and finish my meal. And so there's a specific ordering where perhaps we don't have deadlock here, just because of the way that people choose to pick up their chopsticks. But this is not, necessarily guaranteed. So there does exist an ordering where we have deadlock. There exists another one where we don't. And so a lot of times you might see that if your program is prone to deadlock, sometimes you may run the program with no problems, and other times it might hang because the order in which threads executed resulted in deadlock. Yeah, so you can get lucky, but you may not necessarily. Okay, I'm gonna stop this video and go over the 4 ways to handle deadlock in another one. So hopefully that was helpful, and see you in the next one.